Welcome back. In the previous lecture, we explored the properties of the 2-qubit singlet state, which is a maximally entangled state. In this lecture, we talk about maximally entangled states more generally and learn that systems in pure states cannot be entangled with other systems. So in previous lectures, we were using this singlet state for qubits, discussing how a statement about Bell's inequalities comes about from the quantum mechanical reasoning. And we called this a maximally entangled state. It was a maximally entangled state of 2 qubits in this case. So here we have one of the qubits in the state 0, the other one in the state 1, and here's the other way around. But we have a combination of these two, a superposition of these two possibilities, here with a minus sign, but it's not a minus sign that's important. What is important is that we have the 0-1 state, where each qubit has definite properties described by the labels 0 and 1, and we have the 1-0 state, where each qubit again has definite properties, but the superposition of the two states, which gives us the singlet, has properties which are quite different from the properties of these individual states. This is a bit unusual, but it's not completely unusual because we know other examples of this kind. When a chemist takes 2 grams of hydrogen and 16 grams of oxygen and puts them together and ends up with 18 grams of water, then the water is a very familiar but also quite complicated substance that has many properties that the hydrogen gas and the oxygen gas that we start with cannot possibly possess. So this is also the case here. The 0-1 state has very definite properties for the qubit 1 and the qubit 2, and the 1-0 state also has very definite properties for each of the qubits. But the superposition is a new thing where these qubits have lost their individual meaning. Just like in the water molecule, we have oxygen and hydrogen, but then they form a new entity. They are no longer oxygen and hydrogen. They are now together water. So this is an entangled state, and we had talked about entanglement before, but now let's be a bit more systematic and say something about maximal entangled states in general. For that, I will look at two properties, property A and property B. And for property A, we have a basis of kets A1, A2, and so forth, say AN. And for property B, we have a basis of B1 and B2 and Bn. And for simplicity, I will assume that the n is the same. So although property A is a property of one physical object and property B is a property of a different physical object, there should be similar properties in the sense that there are n different outcomes at most of a measurement of property A, and there are also n different outcomes at most if I measure property B in the other system. So the properties A and B, they are like described by the 0 and 1. So the 0-1 here would be an A1 and a B1, and the 1-0 here would be an A2 and a B2, and the minus sign we can incorporate in how we define the ket B2, if that's what we want to do. Now, just like the kets here are made up from tensor products, I can also make up kets here from tensor products. So I can make up kets where I have one of the A's, and then I have the tensor product with one of the B's, say be A1 and B1, and we will just label this as A1, B1. So this is now a ket for two parties, property A for one physical system, property B for the other physical system. And if the joint system is described by this ket here, then property A has the value A1 and property B has the value B1. And of course we can also combine A2 with B5 and so forth if we like. Now, as long as we have the physical system described by this kind of ket, then property A has a definite value and property B has a definite value, and they are like separate properties in separate systems. But something of this kind would be a cat, and now let me call that cat E, and this comes about by taking the cat A1, B1, adding to it the cat A2, B2, adding to that the cat A3, B3, and so we continue until we get to the cat AN and Bn. So in each of these cats, one value of A is paired with one value of B, and we have just chosen them such that they carry the same numbering 1, 1, 2, 2, 3, 3, but that's just our choice in numbering these cats such that we have this matching in these cats that refer to A and B jointly. Now there is n of them, each of them we consider to be normalized, so if we want to normalize the sum of these cats, the superposition that we have created, then we should divide by the square root of n. Now, just like here, I said that the individual cubics no longer have properties of their own. The same is true for this entangled state. And let me just look at the projector that we have from there. So this is now the statistical operator that goes with this cat. And to make my life a little bit simpler, I will write this expression with the help of the summation symbol. So the cat labeled by AJ and BJ, all of them are summed up, and then I divide the sum by square root of n. So this product now is a product of two expressions of this kind. So there are two factors of square root n, which gives me an overall factor of n. Then there is a sum over two indices. Let's call them j and k, and both run from 1 to n. And so for the cat part, we have the AJ, BJ cat. And then for the bra part, we will have the AK, BK bra. And right now I have just written this cat bra that we get from this state in this particular form. And I want to claim that this is maximally entangled. And for that, I have to check the following property. If I ignore one of the systems completely, then the remaining system is in a completely mixed state. So what does this ignoring mean? So for the ignoring, we just look at the statistical operator for party 1 or party A all by itself. Okay? And for that, we take the statistical operator for the joint system and we trace over system B. Now, the trace, remember, had this defining property that if I have a cat, say, X and another cat Y and a bra Y, then the trace of this cat bra is the bracket YX. So we are now applying this to this situation. However, keeping in mind that the trace only refers to the B's, does not refer to the A's. The A's will survive this procedure. So here we are. We made ourselves this entangled state, and now we are looking at the state for property A alone, which we get by tracing out property B. So let's write this out in a bit more detail. So here we have 1 over n, then we have the sum over j and k, and then we have the trace, but only for the b part, of aj, bj, ak, bk. So remember that the trace b only refers to the b part here. So to be a bit more detailed, let me just remind ourselves that this is really a tensor product of aj tensor bj for the cat part, and the tensor product of ak tensor bk for the bra part. And now the tracing is for this part. And so on my piece of scratch paper over here, I look at the trace, and this is only for the B part. And what I am tracing is Bj and Bk. And that is the Bk Bj bracket. And since these are kets and bras from an orthonormal basis, we will get delta jk, the Kronecker symbol that says it's 1 if the indices are the same, and is 0 in all other cases. So this is on our piece of scratch paper. We use this in here now. So we will have the aj and the ak contributions survive the tracing. So there is the aj ket surviving, there is the ak bra surviving, and the bj ket and the bk bra, after tracing out over b, will give us the delta jk Kronecker symbol. And now this is 0 except when k is equal to j. As a consequence, then this sum over two running variables, j and k, two indices, will collapse into a single sum. And that single sum is just 1 over n times the sum over j, say, of aj, because we only get a contribution when j and k are the same index. So we have the same index j twice now. But this sum is the completeness relation for the ages. The completeness relation says that this sum is equal to the identity. So we get 1 over n times the identity for the state of property A all by itself. And this is, as anticipated, the completely mixed state. Now, since everything is nicely symmetric between property A and property B, it is clear without a separate calculation that also the state for property B all by itself, which we get by tracing out property A from the entangled state that we have constructed, that will also be the completely mixed state, but now it's the completely mixed state for property B. So, a pure state which is such that after tracing out one of the two parties ends up with a completely mixed state. A state of this kind is a state that we call maximally entangled. Now, we have seen this example for just 2 qubits before, but in the more general situation, the structure of a maximally entangled state is like this. So we have a maximally entangled state constructed like this, and all maximally entangled states are of the same kind. In particular, I can apply a unitary transformation on either the property A or the property B, and that will just convert the basis that I have for the A property into another basis for that degree of freedom, but it will not affect this structure as a whole. And if I do a unitary transformation on the B side, then it will just convert the basis that we have for B here into another basis for the property B, and will not affect this structure as a whole. So we have a maximally entangled state, we do a unitary transformation on one party or on the other party, we end up with another maximally entangled state. Technically speaking, this statement is that local unitary transformations, the ones that only affect property A or property B, that such local unitary transformations turn maximally entangled states into other maximally entangled states. More generally, whatever entanglement properties we have, they are not affected by local unitary transformations, because entanglement is a property of the joint system. It's not a property possessed by one system all alone. So I was mentioning that any kind of entanglement we have, and yes, I mean, here we have a maximally entangled state, But one such term by itself, one term of the kind, say A2 combined with B5, if that's the state of the system, then that would not be entangled at all. So here, system A has a particular property, a particular value A2, and property B has a particular value B5, and there are no correlations between the two. Whereas here, in the entangled state, if I should measure system A and I find property A1, then system B will show property that goes with the label B2. And likewise, if I find another value of A, there's a corresponding value for B. Just like here, if in Alice's measurement she finds a 0 for her measurement, then the corresponding measurement for Bob will necessarily give the answer 1, and vice versa in the second term. So here we said, well, we have an entangled state, we trace over, we get a completely mixed state. If we have this state and we trace over 1, then we get a projector. So if I take this state, say A2, B5, to stick with the example, A2, B5, and I trace out property B, and then what is left is the A2 projector, and that describes a pure state. And likewise, if you trace out property A, then you end up with the B5 projector, and that's again a pure state. So here's a question. If I have a state described by some kit, and I trace out one of the parties, say I trace out B, and I end up in a pure state for property A, is there any entanglement to begin with? Well, let's see. So we have some state of some structure. I'm not specifying it right now, but we want it to be such that if I trace out property B, then we have a pure state for A. Say we want to get A1, yeah, as an example. Just some pure state. Yeah? And this pure state will be represented by a ket and a bra in some basis, so why not use A1 for the example, since we have that basis already. So what kind of property can I have for those states? Well, the more general state of this kind, the question mark state, if we write down the most general thing that we can think of, well, it will be a sum over j and k, both running from 1 to n, and I will have aj combined with bk. So all n squared combinations, not just the n combinations that appear here, but all n squared combinations of this kind. And then there will be coefficients psi jk. Well, so this is the most general two-party ket that I can make in this situation. And so let's see what happens if I trace out property B. So let's work out what is the trace over B of this question mark state that we have written down on the right. And so we will get the sum over j and k from 1 to n. And then we have the trace over B of aj and bk, and then so that's from the ket part, but from the bra part we will have also sum over, say, L and M, also going from 1 to n, and there will be AL and BM, and then we have the psi jk that comes from the ket part, and then we have the psi LM complex conjugate that comes from the bra part. Now we trace out property B, and that will produce a Kronecker delta for K and M, and it will leave the AJ ket and the AL bra as leftovers. So we have finished with this, and we have the sum over J and K and L from 1 to n. The M sum I will convert into K, as we have this Kronecker delta symbol here. So what we will have is AJ ket, this left over, we have the AL bra, and we have the coefficients psi JK and psi LK complex conjugate, and here is the leftover AL. So after cleaning up the board and giving us some space to write, let's see where we stand. This is the general expression, and we want to reconcile it with this outcome that we want to have for the tracing. So here we begin with a general state that is we just label by the question mark, and it's specified by deciding on the values of these coefficients psi jk. But in the final expression, we only have the A1 ket and the A1 bra, which means that from all the kets that appear here, only the one with j equals 1 has to survive the summation, and also only the bra with the label L equals 1 can survive the summation. So all terms where j is not 1 or L is not 1 have to vanish, which means that the psi's have to vanish, except for those where j is 1 and L is 1. So from this general expression, then we have, so this is from the general expression, we have, and now we put j equals 1 and n equals 1, so we still have the sum over k from 1 to n. Here is a1, and then we have the psi 1k and the psi 1k complex conjugate, and here is a1. And this is the a1 ket, the a1 bra, and in between, well, we just have the sum over k from 1 to n of the absolute value of psi 1k squared. Right? And so this sum, therefore, has to be equal to 1. Now, returning to the expression for the question mark, what do we have? So now what does this tell us about the question mark state? Well, the question mark state, as we wrote it down, was a sum over j and k from 1 to n. And here we had a, j, and bk, and the psi jk coefficients. But now we know that the psi jk coefficients with j not equal 1 are all 0. So we just simplify this to the sum over just one j value, and we still have the summation over k. And here we have the a1 and the bk ket and the psi 1k coefficient. Now each of these kets is the tensor product of the a1 ket with one of the bk kets, which means that the a1 ket is a common factor for every term in the sum. So we can just take it outside the sum. And then we have a1 times the tensor product of the sum, where k equals 1 to n. And here we have bk, and here's psi 1k. So this is a linear combination of the bk's with coefficients which are such that when we square them, they add up to 1. Which is to say that this is some normalized bket. Let me call it b prime. So in the end, the question mark state turns out to be of the structure A1 tensor the b prime state. Whatever is the b prime state, that depends on what are these coefficients, but whatever these coefficients are, we have some linear combination of the b states. And that is to say, if we insist of having a pure state for system A after the tracing, then we have a tensor product state to begin with, and there is no entanglement. Okay? No entanglement. in the question mark state, if the question mark state has the property that if I trace out one of the parties, we get a pure state for that party. So now, having observed this, we recognize that this maximally entangled state for parties A and B is also a pure state. So since the two parties together are in an entangled state, there can be no entanglement with a third party. So colloquially speaking, if Alice and Bob are maximally entangled, then they cannot also be entangled with Charlie. And this property that pure state cannot be entangled with anything else, that has become known as the entanglement monogamy. Let me just write this down. It's one of these terms that are acutely chosen, but they really mean something very simple. In this case, it means if you have a system, even a composed system of two parties or more parties, and that's in a pure state, then it cannot be entangled with anything else. In summary, local unitary transformations turn maximally entangled states into maximally entangled states. Further, entanglement monogamy does not permit entanglement between a system in a pure state and any other system. In the next lecture, let's look at indistinguishable particles.